Hello, welcome to Calculus by Dr. Oz. Today we're starting a brand new topic called limit. In fact, calculus, the modern calculus, starts with the limit concept. Today we're going to specifically talk about finding limits graphically and numerically. For the regular calculus sections, I have two objectives to achieve today. The first one is the estimation of a limit using a numerical or graphical approach. And second, we're going to learn different ways where the limit fails to exist. For honors sections, in addition to the first two learning objectives, we were going to have also another one, which is the study and use of the formal definition of limit. In other words, we call it epsilon delta definition of limit. All right, I want to introduce the limit concept on a very cool example. Here we go. We have the f of x, x cubed minus 1 divided by x minus 1. And this is a rational function. And we know that the domain of this function is all x's from negative infinity to 1 and 1 to infinity, because x equals 1 makes the function 0 over 0, which is undefined. So we have to exclude 1 from the domain. Now we can graph this function for all x values except 1, because as I said, we don't have the function defined at x equals 1. We still want to know the behavior of the function around 1. So what we're going to do here is to approximate 1 from the left and right to see how the function values behave. So for that reason, we have a table of sample values. So our target value is 1, so I'm going to the right and to the left of that. And the choice of these numbers here all depend on your taste, by the way. So on the left, I picked 0.75, 0.9, 0.99, 0.999. If you want to add more points in between, just do it. If you want to, you can add also 0.999, 4 nines, and on and on and on. It, again, depends on your taste. And on the right, we have 1.001, 1.01, 1.1, and 1.25. I don't want to go too far because it's not going to allow me to understand the behavior around x equals 1. So essentially we're going in this direction and in this direction and checking the function values. And I call this table as a table of sample values. So all you're going to do here is to evaluate the function f at each sample point. For example, from this table you can read that f of 0.75 is approximately equal to 2.313. So you can use your calculator for function evaluations. Or f of 1.01 is equal to approximately equal to 3.030. And please fill out the table of sample values and see what the function values approach when you get closer to x equals 1. And from this table I can see that the values are increasing in this direction to 3, and the values are decreasing in this direction to 3. So in other words, if you add more sample values in between these points, right? So if you add more sample values, that means you're getting closer and closer to the value 3. All right, here is the graphical representation of the rational function x cubed minus 1 divided by x minus 1. Remember that at x equals 1, the function is not defined, so that's why we have a punch here or hole, okay? But we can still graph it. We can still graph the whole function. And from this graph is you see that when you get closer to 1 from the right or left, okay, so the corresponding function values approach 3, okay? So we're walking in this direction and this direction, so that means we're getting closer and closer to 3. And I have a cool Desmos representation of this. Let me just show that to you. Here you go. Here is our x equals 1. As you see that down there, x equals 1. As you get closer to 1 from the left and right, as you see that you're walking on the red curve, so you're getting closer to the value 3. All right, that's pretty cool. We can see like where the function values approach. All right. Well, to represent this limit behavior, we're going to use a notation, limit notation, which is right here. So we write lim, and we have the x approaching 1, that arrow telling us that x tends to 1, and we're looking at the limit of the function f of x here. Okay, and the way we read this is like the limit of f of x as x approaches 1 is equal to 3. So this number 3 here, came out of the table of sample values. And this limit notation is all over in calculus, so it's better to get used to. And we say like a limit of the function as x approaches c, from either side, by the way, from either side, either from the left or right, is supposed to be equal to L. That's what this definition says. And recall that in the very first learning objective, we were supposed to use a numerical or graphical approach to estimate a limit. That's exactly what we're doing so far. And I'm going to go through another example here. So that's another rational function, x over radical x plus 1 minus 1. And we're looking at the limit of the function near x equals 0. Okay, so in other words, with the limit notation, what is the limit of this rational function as x approaches 0? All right, have your calculator ready and have a table of sample values. So the target x point is x equals 0. So we're going to the right, to the left of that, but getting closer and closer. So my big value, the biggest value here is like 0.01, and smallest value is negative 0.01, and I choose negative 0.001, negative 0.0001, and similarly, I take symmetric points around x equals 0. And as I always say, you can add more points if you want to. So, for example, you can add 0.1 here, you can add 0.00001, and you can do the symmetric version of that on the other side of 0. And the next step here is to evaluate the function by using your calculator at the sample points. For example, I can easily read that f of negative 0.01 is approximately equal to 1.99499. Okay, so essentially you're plugging in here negative 0.01 for x and let the calculator approximate the function value. So to convince yourself, please use your calculator for all of those values and make sure like you get those numbers on your way. And the question here is that, is there any pattern for the values of f as x approaches 0 from the left or right? So I can check that when I go in this direction. I'm getting closer and closer to 2. In fact, the values are increasing to 2. And on the other side, I am going down to 2. Essentially, the values are decreasing to 2. So this tells me that the limit value should be equal to 2. You can go ahead by using just the table of sample values. You can go ahead and write that this limit is equal to 2. And let's convince ourselves graphically as well. And remember that x equals 0 makes the function undefined. Still, 0 is not in the domain of the function. You can see it right here. When you plug in 0 for x, so f of 0 is 0 over radical 0 plus 1 minus 1. That is going to take you to 0 over 0, which is undefined. For that reason, x equals 0 is not in the domain. So we have a punch here, as you see. We have a punch here. But if you get closer to 0 from the right and left, that means you're walking on the curve on the right of this punch here. So that means you're going in this direction and getting closer to this value 2, and then you're walking in this direction, getting closer and closer to the function value 2. So as a final remark here, so even though the function is not defined at x equals 0, we can still look at the limit of f, and that limit exists, and essentially it's equal to 2. And this happens all the time because in this chapter we're going to have functions where the function is not going to be defined at the given limit point, but we can still check where the function values approach around this point. All right, please move on to my next video to learn about the cases where a limit can fail to exist.